Okay, you can mute yourself. This is the problem that we are going to discuss now. Is like a sleeve and cotter joint. See this red color portion, we call it as sleeve. Red color portion, we call it as sleeve. And this pins, we call it as cotters. And here, up to here, this is half of the shaft that belongs to one component, and the rest belongs to other component, the other half of the shaft. Okay, here this is sleeve and this is cotter. Half of the sleeve is being inserted by one shaft, other half of the sleeve is being inserted by other type of shaft. If not, the shaft belongs to the other component. Okay, now our aim is to design this sleeve and also this cotter and also the shaft. Sleeve, cotter and shaft. These are the three components that we have to design in this particular component. Okay, in the previous one, it is socket and spigot. It is socket and spigot. The diagram representation will be different for that. Anyway, let us go with this problem as we are discussing about sleeve and cotter. Okay, but here the design procedure and some of the formulas are almost similar with respect to socket and spigot joint. Okay, now here it is given as it is having a tensile load of 60 kilonewton, thereby P is equal to 60 kilonewton, nothing but 60 into 10 to the power of 3 Newton. All parts are made up of same material. That means we will not be going for different types of yield stresses. We will not be going for different types of tensile or crushing stresses. For everything, stresses will be same. That is here tensile stress, either it may be compression or tension, that is equal to 60 megapascal. Okay, 60 megapascal will be represented as 60 Newton per millimeter square. Okay, actually it is Newton per meter square. Actually it is Newton per meter square. Any doubts from anyone? Somebody has raised his hand. I don't know why. If you have any doubt, you can ask me. And next, it is shear stress. Shear stress is equal to 70 megapascal, which is given in the question. We will be representing it as 70 Newton per millimeter square. Similarly, crushing stress, sigma C. Crushing stress, sigma C. Sigma C is equal to 125 megapascal, which is equal to 125 into 125 Newton per millimeter square. 125 Newton per millimeter square. Okay. Now, just here, as in the previous case, we will be designing one after the other. One after the other. Okay. As in the previous case, we have to design 4 components. That is sleeve, that is socket, spigot, cotter, and also the shaft. Whereas in this case, we will be designing only 3 components. That one is shaft. We have to design shaft. Second one, we have to design sleeve. The third one, we have to design cotter. 3 components. If we design 3 components, that is sufficient. Okay. See, for designing shaft, we will be having a common formula for all types. That is, first step is we are going to design the shaft. That is design of rod. Design of rod. As the P is perpendicular to the shaft, P is perpendicular to the area of cross section of shaft, thereby force is equal to pi by 4 d square into normal stress. Okay, here we want to find the diameter, thereby d square is equal to 4p. D square is equal to 4p by pi into sigma, which is 4 into p value is 60 into 10 to the power of 3 by pi into sigma value, that is tensile stress, 60 kilonewtons. 60 Newton per millimeter square, sorry. Thereby you will be getting diameter is equal to 36 millimeters. 36 millimeters. Okay, I think everybody is clear. See here, we have designed our first one. That is, we have designed our shaft. Okay, now the thing is that we have to design our sleeve. And also we have to design our cotter. Okay, let us design cotter initially, then we will be going for the sleeve. Okay, If not, let us design them cumulatively, one after the other. The second one is that I am going for diameter of, if not width of the quarter, if not width of the quarter. Okay, that is here I am writing that diameter of enlarged end, enlarged end of rod, and also we will be determining about thickness of quarter. We will be determining about thickness of quarter. This is enlarged one, D2. Enlarged one, D2. D2 is that enlarged one. Okay, and also we will be discussing about thickness of the quarter. Okay, similarly, we have a common formula for that. We have a common formula for that. That is P is equal to pi by 4 d2 square minus d2 into t, which will be multiplied with shear stress, which will be multiplied with shear stress. Just now substitution. Okay, we know what is P, we don't know what is D2, we don't know what is D2, even we don't know what is T, but we know what is sigma. We know what is sigma. Here unfortunately there are two unknown components, so that we will assume one component, that is assume T is equal to D by 2 by 4. Okay, this is an assumption because there are two unknown terms. Okay, you can assume accordingly. Okay, let us go. Let us substitute this one. That is P is equal to pi by 4 d2 square minus d2 into d2 by 4 into sigma, which will be giving us P is equal to pi by 4. Here d2 square I will take common. D2 square I will take common, minus 1 by 4. D2 into dt will be coming d2 square, which I have taken as common, into sigma. The thing is that we have to find out d2 square. The thing is that we have to find out d2 square. The thing is that we have to find out d2 square. Okay, anyway, the thickness has been attached over there. I cannot shift that figure now. That is d2 square is equal to p by pi by 4 minus 1 by 4 into shear normal stress, that is 60 into 10 to the power of 3 by pi by 4 minus 1 by 4 into normal stress. Normal stress is also 60. Okay, normal stress and also the force both are same, 60 and 60. By this you will be finding d2 value. D2 value is equal to some 44. Similarly, as it is d2 is equal to 44, t is equal to d2 by 4, thereby it is 11. Okay, see here, I have found out thickness of the quarter also. Thickness of the quarter and also internal diameter of the sleeve. Not only one, internal diameter of the sleeve also I have found out. Okay, internal diameter of the sleeve, that is d2. If you see over here, internal diameter of this is sleeve. If this is sleeve, this is internal diameter and this is external diameter. Internal diameter I have found out, that is d2. Similarly, I should find out external diameter. If you see, external diameter is nothing but d1. Okay, that is what I will do now. That is what I will do now. That is, third one is that outer diameter of, if not outside diameter or outer diameter of sleeve. That is P is equal to pi by 4 d1 square minus d2 square minus d1 d2 into t, which is multiplied with shear stress, which is multiplied with normal stress. Here in this formula we know what is P, we know what is D2, we know what is D2, we know what is T, and we know what is shear normal stress value. The thing is that we don't know what is D1 value. Okay, here finding D1 is a bit complicated. Anyway, you have to find that value. Here 60 into 10 to the power of 3 is equal to pi by 4 d1 square minus d1 square we don't know, thereby pi by 4 into d2 square. D2 square is nothing but 44 square minus d1 value we don't know, thereby d1 into t. T value we know that is 11t. So it will be 11 into d1 minus d2 into t. D2 into T. Thereby D2 value is how much? D2 value is 44. 44 into 11, which is whole multiplied by whole multiplied by normal stress. Okay, thereby I will bring that normal stress over here. Normal stress is equal to 60. 60, 60 will be getting cancelled. Okay, just do simplification, that is pi by 4 d1 square minus 11 d1 minus, if not, write it as plus, minus pi by 4 into 44 square minus 44 into 11 and also minus 10 to the power of 3. If you calculate this in the form of, this is in the form of ax square plus bx plus c in your calculators, just you go for shift to mode equations. Shift to mode, in that you will be having equations. In equations, select this form and instead of a is equal to pi by 4, b is equal to minus 11, c is equal to total equation, that is pi by 4 into 44 square minus 44 into 11 minus 10 to the power of 3. Substitute these values, you will be getting d1 is equal to 60 millimeters. d1 is equal to 60 millimeters. Okay, we have designed capital D1, that is outer diameter also. Now we have to design width of the shaft. We have width of the cotter. We have designed thickness of the cotter. Now we have to design width of the cotter, that is B value. Okay, now width of the cotter, we have a formula, that is P is equal to 2BT into shear stress. That is P is equal to 10 to the power of 3, 60 into 10 to the power of 3. 2 into B value is that we have to find T is 11 and also shear stress is equal to 70. If you calculate this, B is equal to 60 into 10 to the power of 3 by 2 into 11 into 70. Thereby you will be getting B value, that is width of the cotter is equal to 40 millimeter. Width of the cotter is equal to 40 millimeter. Okay, similarly we have to design about the distance of the rod from the beginning of the cotter and also from the end of the cotter. That is fifth one, it is just two steps away from our answer, that is distance of rod from beginning to the cotter end, to the cotter cotter hole, okay, I will show you in the figure. Here, this one, from here to here, this is what we are going to find, A value. Okay, similarly we have to find C value also, that is from here to here, that is C. Both values if you find out, our answer will be completed. That is P is equal to 2A D2 into shear stress. Okay, now we have to find out A value, thereby A is equal to P by 2 D2 into shear stress. We know what is D2, we know what is P, and we know what is shear stress. That is 60 into 10 to the power of 3 by 2 into D2 value. D2 value is I think 44 into shear stress. Shear stress is 70. Okay, just follow this, you will be getting A is equal to 10 millimeters. Similarly, sixth one, that is distance of rod end from its end to the cotter hole, that is C value. That is P is equal to 2 into D1 minus D2 C into shear stress. Okay, I think we know every value except C value. Thereby C is equal to 60 into 10 to the power of 3 by 2 into D1. D1 is nothing but 60 minus 44 into shear stress is 70. Thereby C is equal to 28 millimeters. Okay, if you observe this here in this particular form, crushing stress is not necessary. In this particular form, crushing stress is not necessary. Okay, just write it down in your notebook. Anyway, I will be sharing the link of this video recording. Go through that and practice some problems. Okay, thank you. You can join for the other session. Those who are present, I have taken screenshot of this. Those who are present, I will be posting in the group.